It's 4 p.m. So it is my pleasure to announce now a talk by Professor Adam Sikora from Macquarie University. This is an analysis of PDE seminar, but perhaps I can say that analysis was underrepresented in this seminars, and now we have a talk about square functions and Riesz transforms. So this is the heart of modern harmonic analysis, and we will learn from Adam about some new results in this area. Please start.
Thank you very much. So indeed, my talk is more say concentrated rather on analysis than on PDE, even though I always think about analysis being justified by PDE. So if your analysis stops having kind of connection with PDE, that's you should kind of be careful. But nevertheless, yeah, I mean, what I want to talk about is well, there is some PDE in the background, but essentially this is talk about analysis, and particularly about harmonic analysis. So there's kind of like a typical kind of harmonic analysis notion of square functions and Riesz transform. So actually, what I want to talk here is more, maybe a little bit more about on the square functions, because this is new. So about the result about Riesz transform is probably like 2 years old, and I'm interested here in something which I describe in a moment in this class of non-doubling manifolds, and try to develop harmonic analysis for this class of objects, right? And as an add-on on discussion of Riesz transform, I want to add discussion of square functions, which is somehow complementing and developing the idea of Riesz transform. So, so we are considered a class of manifolds. I will talk about this a bit more. Obtained by taking the connected sum of finite number of n-dimensional Riemannian manifolds. So we've got a kind of like just Euclidean space Rn, right, here, with a standard metric, Riemannian metric, Euclidean metric, right? And we've got compact manifolds. We kind of like, we keep them in a sense for technical reasons, because we want to connect them. And to do so, kind of, it's nice that they will have the same dimension. But on the other hand, the dimension infinity, if you look at the behavior of, say, of the volume of the ball, which are large, right, will be connected to the Euclidean part. So this will be kind of given by this number ni here. And well, so one of points of significant interest here, when all these dimensions are not equal, because then the space is not doubling, and doubling condition is one of pretty much necessary condition in every aspect of harmonic analysis. So this is kind of like getting out of this condition is quite interesting. And what we're going to do here, we're going to describe the range of exponents p for which Riesz transform and vertical square function, as well as horizontal square function, which I forgot to add here, are bounded as an operators on LP of M. So let me start, before I will start kind of like explaining myself and building some intuition, I want to say a few words of technical introduction. So first of all, I want to define, say, vertical square functions. So here I'm taking Laplace-Beltrami operator acting on my manifolds, or just if you wish, you can think at beginning that just your manifolds is just Rn, right? And I'm taking gradient of this, say, resolvent of order capital M here, and apply this to function f, and then I integrate this from 0 to infinity. You could kind of like quite easily check that this is kind of this or other way isometry on L2. So if you calculate SF on, say, on L2, this will be with constant, or will be proportional or even equal to just L2 norm of function f. And as usually in harmonic analysis, you would like to ask where this is the case for other p. And we actually proved here that this is true with p between 1 and minimum of dimension at infinity. So I will explain this a little bit better. So this subject is quite related with Riesz transform, and it's also kind of a way to define Hardy spaces, right? So one of definition of Hardy spaces is that you define norm of function f in, say, in Hardy space H1 being to, or HP being equal to the norm of square function in LP, right? And from what you see here, then in our setting, this would mean that this Hardy space is just LP space for, say, this range of P. But quite interesting is case P equals 1. So then this space is actually always slightly different. And this is kind of like classical topic in harmonic analysis. This is kind of one of motivation why I'm interested here in harmonic in square function. And there is another definition which you could in which you could define square function, but in which you replace gradient just by the operator, right? So this is just a little bit of different scaling. So instead of having here t gradient, t nabla, I'm replacing this by t square Laplace operator, right? And Laplace-Bertrami, if we talk about HP, about our manifolds here, right? And we again define square function in a possible in a similar way. And here the difference is that we replace gradient by the Laplace operator. So if you are on Rn, then all this definition of vertical and horizontal square functions are essentially equivalent. So the kind of LP norm will be equivalent. And here, one of interesting point, one of kind of different situation is that actually here, this is not the case, right? So this horizontal square function is bounded for all LP spaces, right? And weak type 1, whereas this vertical square function is bounded only in the range. So this is a kind of like a point of interest here. Okay, so let me just say a few words about geometry, about the world in which we live. So here I'm start with a nice picture of geometrical surface, which is called catenoid, but well, it's essentially this is like a connection of two planes. So from our point of view, from point of our analysis, this picture is very similar to the next picture, right? So this is my realm, right? This is kind of world of space in which I'm interested, right? So here I've got a plane connected with a plane, and in a sense, here you could kind of think that this is a kind of like a small perturbation, right? So you've got two planes which are living separately, and then you can do an analysis on one and the other, right? So nothing really interesting happening there. But then we make a small compact perturbation. We connect them with a bit of a manifold, right? And then actually, interestingly enough, analysis starts to be very, very difficult. So let me just show you another picture. So this is a picture where I connect cylinder with a plane. So this picture is one of point of interest here with this object here is that we've got the ball living in the cylinder side. When we take a very huge radius, its volume behaves like, of course, first power of the radius, right? And if we are on the plane, it behaves like r square. If you look a little bit, what does it mean? It means that the space doesn't satisfy a doubling condition, right? So that's one of points of interest here in this discussion here, one of main interest. Okay, so let me start talking a little bit more about Riesz transform, about motivation. So I guess, you know, talking about why you want to study harmonic analysis, right? Because of PDE, as we said before, right? So, and so let's start off kind of like why we interested in Riesz transform and what is actually Riesz transform, because I have not explained this yet, right? So we can define Laplace-Bertrami operator, right, as using quadratic form techniques, right, and just using gradient, right? So we can also kind of, with a little bit of algebra here, or this or other way, we can write it down as a delta 1/2 of f times delta 1/2 of g, right? And then you end up, if you just think about functions, one function, then you end up with situation where you can see that delta 1/2, right? So half of a Laplacian in L2 is equal to the gradient of f in L2, right? And now the Riesz transform, the basic question of a Riesz transform is the question, what if you replace, can you replace 2, right? Can you replace it by arbitrary p between 1 and infinity? And the answer is almost yes, right? At least you can do it definitely for all p strictly between 1 and infinity. So for a classical Riesz transform, so if we start for Rn, right, for standard Laplace operator, then it's true that for any p, gradient of f can be estimated by 1/2 of norm of f in LP for all p between 1 and infinity. Here, actually, this is kind of like, this is main point. It's going to be somehow different. So this is like what is quite interesting in the situation of this manifold with ends, which we discuss here. But okay, before we go any further, let me say a few words how to think about this result. So this is a little bit of a results with you kind of, when you do PDE, right, you want to know that you want to have some regularity results, right? So you know that, say, if your Laplacian of f is equal to 0, you know that f is smooth, right? And so if you know some kind of, say, if you know that Laplacian of f is in LP, can you actually, does it mean that you can calculate all the parts of this Laplacian? So can you then really calculate all the partial derivatives which you need to define Laplacian? And the answer is somehow yes, almost yes. And this is, so to say, kind of the Riesz transform itself is a little bit like a precise statement of this, and in the kind of, in a sense, in a simplest way. So we've got just, say, first derivative gradient, right? And we compare it with, say, so to say, first order operator, right? You can talk about here, I don't know, you can use notion of pseudo differential operator, something like this. So we've got this first order elliptic pseudo differential operator, and then it turns out that if you can calculate this operator of function f, say in some LP, then this function has meaning for all first order derivative in LP, right? So I would say that this is like really natural motivation coming from regularity theory, right? So we want to be able to calculate gradient, calculate somehow Lipschitz continuity of some functions, knowing that this function is solution of this or other PDE, right? And this is like most, in a sense, the basic block of such estimates, which is in a sense very precise, right? So, and the answer the answer usually, the answer which you expect is that, as I said, that this should be something which is bounded for all P, right? So that's a bit of a motivation of Riesz transform. So Riesz transform, before I go to you see my next point, which is a doubling condition, Riesz transform is so-called singular operator, kind of Calderon-Zygmunt type kernel, right? So this means that actually you definitely do not hope for this to be true for p equals 1 and p equals infinity, but it's kind of like failing p equals 1 and p infinity just slightly bit. But what is another point which I would like to mention here is that when you talk about singular integral operators, when you talk about Calderon-Zygmunt kernels, then your basic tool is doubling condition, right? And here we do not have doubling conditions, so our discussion became somehow more difficult. So we are losing this kind of basic assumption from harmonic analysis. Unfortunately, fortunately, we kind of our situation is maybe not as bad, because you still can think about this as a being small perturbation, right? So, but essentially we're losing this condition. So, you know, pretty much in every book in harmonic analysis, right? So, say, I don't know, if in Stein or something of that type, you will sooner or later, rather sooner than later, I would say, you will end up with the definition of a doubling condition. And this is like a very natural condition. It's essentially, it says that the volume of the ball is kind of like, behaves like a polynomial, right? But yeah, it's not quite enough. So we've got this situation here. So when the ball of twice radius can be estimated by the volume of the ball with radius r, right? So so for Rn, for Euclidean space, this is something very obvious, right? Because then you will have just here you will have equality, right, with 2 to the n, right, power, right? But for many other objects, you've got similar estimates, well, with doubling condition, and essentially this condition fails for manifolds with n's if n's has different dimension. So as I said before, if we look at this say example of cylinder connected to a plane, right, then the ball here behaves like r square, right? So like radius v, say mu of b xr, here behaves like r square, and here behaves like r. So if you take a ball of radius r on one side, right, and then you take a ball of radius 2r, then the ball will kind of get on the other side, and it will start to have volume of, instead of r, it will start to have volume comparable with r square. So taking r large enough means that whatever constants you have, it will fail. So that's somehow the doubling condition, and this is one of point of interest, right? So in harmonic analysis, I will not talk about this, but yeah, we kind of we try very hard to obtain some results without doubling condition. It's usually quite difficult, but it's somehow interesting condition to understand, and to understand its role in harmonic analysis. Okay, so I should mention here somehow quite significant, say, starting point. It's not exactly really starting point, because before Grigorian and Salov-Costa, there were some papers of Davis devoted to notion of manifolds with ends, but Grigorian and Salov-Costa, somewhere around I guess 15-20 years ago, started to study manifolds with ends, especially heat kernels on manifolds with ends in quite systematic way. And so interestingly enough, they have really beautiful and powerful heat kernel estimates. But this, and so you would kind of think that actually if you know harmonic analysis, then you'd kind of think that, okay, if we've got a very good heat kernel estimates, then getting boundness of Riesz transforms should be quite quick and straightforward. But unfortunately, it doesn't work that way. So somehow a problem with estimates of Grigorian and Salov-Costa is that they kind of impossible to calculate gradients of the heat kernel, which is kind of essential. And because of lack of doubling condition, this actually very quickly, well, the proofs breaks. So it's kind of like, these are very interesting technique, but, and very beautiful results. One advantage of this result is that actually they kind of like more general. So you know, it's kind of like actually there's larger class of geometrical objects which they can consider, but so far these techniques kind of cannot be applied to harmonic analysis, right? So that's a little bit of a problem. Okay, and now let me formulate the first result. So we've got statement about Riesz transform. So this is kind of like a result which is almost 2 years old, right? So we've got, once again, we've got here this manifolds with ends, right? And slightly different than the picture which I gave you before, right? We've got this dimensions of at infinity has to be bigger or equal than 3. Of course, I had a problem with drawing pictures of dimension bigger or equal than 3. So this is why I kind of give you an example of dimension infinity 1 and 2. But actually, it is somehow easier to analyze larger dimensions than a smaller dimension, right? So actually, so this assumptions here that Ni is bigger or equal than 3 is in a sense technical, but so we expect version of its results to be valid for any dimension, but this requires well, you have to overcome significant technical difficulties, right? And so the first point which I would like to make here is that the Riesz transform in this case is not bounded for all p. So even in this case, if you take two connected planes, right, or two connected R3s, and which you still have doubling, but then still Riesz transform is not going to be bounded for all p between 1 and infinity, but only for some range starting from 1 and going to minimum of dimension at infinity. That's in a sense quite surprising and statement. What I would like to understand, which I don't quite understand here, so to say, is that, well, so this is kind of like, I understand this in terms of geometry, right? But I don't quite understand this in terms of PDE and say Laplace-Bertrami operator, and what this actually kind of means on the level of regularity theorems. It seems that regularity theorems kind of related kind of to LP spaces are kind of easier where P is close to 1, but not necessarily true for infinity. Well, yeah, maybe it should be something like this. So, as I said, this results is valid if an I is bigger or equal than 3. So, but we also know, and this is results when we've got one more call for here. So we've got the results with Daniel Nix, which consider the case where, say, n1 is equal to 2, right? And then the answer is that the operator is bounded for all p between 1 and 2, right? So it's, in a sense, you could kind of expect this, right? So if you just look, so the formula is essentially the same, but the weak inequality is replaced by a strong inequality, which is kind of like necessary thing to happen, because p equals 2 is kind of, as we say, it's almost automatic, right? So it's essentially on any manifolds Beltrami and for any Laplace-Beltrami operator gradient in norm of gradient of L2 will be actually equal to to the norm of half of Laplacian, right? So interestingly, the result is kind of essentially the same, but technically this is kind of like quite a lot of additional calculation, additional kind of work to calculate the case where one of the dimension is equal to 2. And I must add it here that actually the results for dimensions, say if you got one end with dimension 1, we actually don't know how to prove the expected results in this case, right? So that's situation for a Riesz transform, and this is kind of a little bit older results. So this is like, I guess, 2-3 years ago. The results with Daniel Nix is a new result actually. Yeah, interestingly, so quite big difference between case two-dimensional case is that when the dimension are bigger or equal than 3, then there is something always like a bounded harmonic function, right? So you could kind of think about if you've got, say, connection of R3 with R3, right? You can think about the function, which is like a probability that you escape, say, from the top end, right? So you've got some kind of function P of X, which is a probability that your process will escape, because it's a three-dimensional case. Then if you just kind of start to get your Brownian motion on the three-dimensional space, then you've got a kind of given probability that you will reach with probability 1 you will reach infinity, right? But if you have two ends, then you've got a function p of x which describes probability of which end you will escape, right? And this function, this harmonic function p of x, will be bounded harmonic functions, which is non-constant, right? So you will have kind of Laplacian on p being 0. And this is kind of quite, in a sense, we think that this is very strongly, there is a kind of idea how to strongly connect these harmonic functions with actually failure of this inequality. And in dimension 2, the function is actually not bounded. It has kind of like a logarithmic behavior, this kind of non-constant harmonic function, so to say. So then the analysis kind of becomes quite different. I will not talk about details here, but I want to talk a little bit about details, right? So the whole proofs, and this will be as well, it's true as well for Riesz transform results as for square function results, starts with a little bit of an observation. So if you've got function v which is compactly supported, and then you look at action of, if you look at this, what we have here, we apply resolvent to function v, end up with function u. And for function u, we can make the following estimates, right? So we can prove the following estimates. So we pretty much, as you for resolvent, as you expect, you've got some exponential decay. The interesting point here is this complementing polynomial decay here, which you get as well, which actually at the end of the day, because somehow we are thinking about crucial point is when k goes to 0. So somehow this decay is crucial. And we kind of like with a rather simple argument, calculation, we can prove estimates of this type, both for resolvent and gradient of the resolvent. So that's in a sense kind of one of big difference between resolvent and heat kernel here. So for resolvent, we don't have much of a trouble with calculating of a gradient of a resolvent as well. So then we construct parametrics, right? So there are 3 points here for the parametrics. So you pretty much, and actually, well, I wrote here 3 elements, but this second element is just like a kind of things which works on the connection, right? So if I've got my picture again, right? So if I've got my plane connected with another plane, right, then this term G2, this will live on this, say, connection, right? So that's, and it actually doesn't really play any significant role in estimates, so to say. Locally, it's kind of behaves like Riesz transform on or square functions on Rn, so that's not something which produce any problems here. And now we've got this part G1. So here this function phi is a function which is kind of like, say, if we've got end I, then this function is equal to 1 on this end, and on the all other ends, it's equal to 0. So this is a kind of like a cutoff function to each end. Because, yeah, we think about this as a perturbation, right? So we've got 2 really disconnected words which are kind of connected with this small compact manifolds, right? So pretty much, which means that you take the operator on one side, you take the operator on the other side. So that's your kind of like a resolvent, right? This kind of connection thing is not that significant. And then you've got the rest, the term, which is kind of the most interesting and most significant one in a sense. And this is the term, which is kind of like a term of interaction between these 2 ends, right? So this term is G3. And actually, this term can be described, right, using this lemma. So this function u here, this resolvent applied to v, this is something which we have here, right? This is again with some kind of cutoff functions. And here we've got resolvents, but this resolvent is a standard resolvent on Rn. So we know very well how to calculate this this object. So we've got, and then the proof is essentially G2 is trivial, G1 is just standard, and G3 is what you have to calculate. And you've got pretty much all estimates needed to be able to calculate this. So yeah, so this is this interaction perturbation part. And in a sense, this kind of inner resolvent things, if you think about it, it's maybe not kind of that apparent from the formula, but if you think about it, this term G3 is a really like a rank 1 operator. So it's something a little bit like you would have phi of z times phi times say times psi of z prime. So you've got a kind of like a multiplication of two functions, right? So this is from a point of view of analysis, very simple operator to understand LP properties and so on. So we still have to go from resolvent to, so this is what I said here before, right? So we've got this term G3, right, is really, and there's missing Z prime here, is like really a term of rank 1 operator. So this is like just a product, kernel of this operator is a product of two functions. So if you understand this, you can pretty much calculate everything, but well, the problem is that you, of course, you've got this k, and you want to understand this simultaneously for all, essentially for all k close to 0. So that's essentially. Let's go back now to vertical functions. So I will not maybe talk more about proof of boundness of Riesz transform. I will talk a little bit about these proofs for vertical functions. So the same way in which we calculate resolvent, we can calculate resolvent of higher orders more or less. We've got a very similar picture. So we've got still kind of like some standard things on every side, and interacting term, which is fortunately rank 1 term. So pretty much based on this description of the resolvent, you can carefully go through a calculation and prove that this function is actually bounded for all p between 1 and minimum of dimensions. And as you expect, so that's somehow kind of things which you expect, that this range of boundness should be the same as for Riesz transform as well. There's actually some abstract results which guarantee something like this, which unfortunately never works for L1 and for weak type things. So which are unfortunately also most interesting one, right? So we've got this notion of vertical square function, and so the result is something which you would kind of expect in a sense, right? So you've got statement which says that in this geometrical setting with which we have, as the square function is is of weak type 1,1 and is pretty much bounded if and only if P is in the same range of which is bounded for if the same range of exponent p for which the function is bounded for Riesz transform. So that means from 1 to minimum. Now for p between minimum and joint to n minimum, we've got also reverse inequality, right? I believe this is just actually this is only technicality. I think this is it should be this first point, the inverse inequality, should be valid for all p starting from 1. And here we've got this another technical assumption. So we have to assume here that the order of the resolvents which we consider is not too big, right? And this is again most likely technical assumptions which I don't know how to remove. And okay, so next I should be close to finishing, I guess. So next we've got the same, as we say before, the same idea with horizontal square function, right? So once again, instead of gradient here, right, we consider Laplace operator, right? And then the situation simplifies quite significantly because we've got everything. So as soon as you forget about gradient, you don't worry about manifolds with ends at all. You've got the same results which you expect from Rn, from standard Euclidean operator, right? So this horizontal square function is actually bounded for all p between 1 and infinity. We type 1, 1 as well, and inverse inequality is also included. So I already said that there's a way of defining Hardy spaces, right? So you define this f HP, right, as norm of say S F in LP, right? So from this one, you could kind of like, you've got another surprising question, surprising observation that actually that say that this, so to say, horizontal HP. So if you think about kind of HP corresponding to gradient and vertical one, so if you think about this HP corresponding to Laplace operator, then these spaces are not equal for P between infinity and this N minimum, right? So that's somehow we don't have situation like this in standard Euclidean setting, right? So that's quite surprising observation. There's actually, so yeah, there is here quite a few points of interest for harmonic analysis. So which comes from this definition, right? So for, as you can see, because of this theorem, this is kind of like for, say, if we are in this range, we've got there's not much of an interest, because then this say norm will be equal to norm of F in LP, right? And your Hardy space, pretty much HP, is equal to LP, right, in this or other range. If we talk about standard operator, this is true for all P. And very kind of interesting case is P equals 1, because then this Hardy space is not equal to L1. But you still have results like results which will say that H1 is not equal to L1, but Riesz transform will be bounded from harmonic from Hardy spaces to L1 space, right? So here I don't know if it's true or not, and also I don't know. So I've got here this I don't know if vertical H1 function is equal to horizontal H1 function, right? So that's kind of the things which I don't know here, and which yeah, I kind of have in mind starting this process, but I didn't manage to understand much of this. Actually, kind of like in the settings, there's a bit of a problem here of proving that actually this definitions are always well designed, right? So for example, like, okay, if this is equal to LP, then this is an easy matter, right? But if not, then we would kind of I don't know if the actually definition of this Hardy space will depend on the order of resolvent which you use in this definition of your square function, right? So there are kind of like a bit of questions here. Okay, and I want to finish, right? So I guess I got a couple of more minutes, so maybe I will finish with this couple of questions. So from a point of view of harmonic analysis, so we kind of get here a little bit far away from LP, but not quite far away. So this is kind of like we are here talking about spectral decomposition of differential operators, right? So we still got some PDE in background, right? And what you would expect is that if you've got a nice smooth function, you will expect that you can define, using spectral theorem or this or other functional analysis, you can define a function f of t of delta, right? Well, such, for example, as exponential function, right? And essentially, you would expect that the norm here, if we assume that function f is smooth enough, it's kind of like that the decomposition should be possible here. So that would mean that the norm shouldn't depend on p, right? So in terms of heat kernel, right? If you start talking about heat kernels with a bit of a complex direction, you would still expect that as long as you do not go into purely complex direction, into purely imaginary direction, right? You still expect that you will have, say, estimates like this estimates at the end, and we don't know if it's true, right? So that's kind of like a problem with what I mentioned before with Grigorian and Salow-Cost results. That, for example, we don't know how to extend them to a complex time, right? So that's bit of a, and maybe I will skip, we don't have much time for this, so I will skip open problem number 2. And yeah, well, so just a bit of literature here. So just about Riesz transform. So Riesz transform is almost 100 years old, right? And it's still, as you can see, quite a bit of a open problem in various directions, right? Then you've got this paper, which I mentioned. This is a very beautiful paper, very interesting paper, Grigorian and Salow-Cost, about heat kernel manifolds with ends. And there are a few more results related to some analysis on Hardy spaces. And maybe I should stop at this point. I've got here, yeah, so I've got here, I forgot, I've got one more paper kind of, which I should mention, which kind of very nicely describe notion of manifolds with ends. So this is Grigorian, Satoshi and Salow-Cost, and the results about Riesz transform are already published, whereas this result, which I mentioned with dimension 2, is still in the process. Okay, great. Thank you very much for your attention.
Thanks, Adam, for a very interesting talk. Are there any questions, comments? Okay.
I have a
yeah. Yes, please.
I have a question. So, could you consider Riesz transform on differential forms and prove boundedness in your setting?
It's possible, but it's still more difficult, right? So yeah. That's essentially, yes. So you know, if you start talking about differential forms, right, you have much more information just from Riesz transform, right? So you can do it, but differential forms are a bit more, yeah, it is more difficult object, right? So essentially, yes. So what we do here, you could try to do on differential forms, but this is it's a very natural thing to do, But
Okay.
if you think about it a little bit, it is a lot of information, right? So you'd kind of expect, and this is kind of a situation that differential forms are more interesting and more difficult.
Okay. Thank
So
you.
for example, even on manifolds with one end and so on, you could, with differential forms, you can end up in a situation where the Riesz transform is not bounded for large P. And then, yeah, there are definitely works devoted to study Riesz transform in the setting of differential forms, right? And they're quite technical, and
Okay.
we definitely would like to know something more about it.
Okay. Thank you very much.
Any other questions, comments? I wanted to ask a question which is, I guess, related to the previous one. In the Euclidean case, you have the whole series of horizontal and vertical functions. Yes, can you think here about estimates for higher order square functions?
Well, there is, well, I guess, in a sense you can, but it starts to be a little bit less natural, So, I mean, from a point of view of horizontal square function, it's taking higher order doesn't change anything. So but for a vertical square function, if we've got a gradient, somehow notion of a square of a gradient starts to be a little bit tricky on manifolds, right? It's not a very natural geometrical object. Here you can in this setting which we have here, you can definitely do it because the ends are Euclidean. So you could kind of, like, if you wish, you can talk about second derivatives and so on. But on general manifolds, the notion of second order gradient is not that natural.
Okay, thank you. Any other questions? If no, let us thank again Adam for a beautiful talk, and let me remind you that we can meet at coffee break after a few minutes. Okay, thank you.
Thank you very much. Thank you for
Thank you, everybody. I will close the session now. Thank you.